Hey, welcome back. Our second lesson in nuclear chemistry today, we are looking at positrons, electron capture, and fission and fusion. So positron emissions. Positrons have the mass of an electron, but the charge of a proton, which is positive. So zero mass, but a positive charge. So hence the term a positron. It's very much like an electron, but with a positive charge. You can use either symbol, just like you could for a beta particle. It kind of is a beta particle, except notice now we have a positive one down below. So instead of a negative one that we had for our beta particles, now we have a positive one. Positrons are emitted when a proton splits into a neutron and a positron, So here's our positron, here's our proton, Here's our proton, and it splits in half into a neutron and a positively charged particle with no mass called a positron. So the charge comes out, it's now chargeless, but it still has its mass as a neutron up here, and that's what this type of decay is. This occurs when there's too many protons in the nucleus. Next up, we have electron capture. So this happens when an electron gets pulled out of orbit. So remember, electrons are kind of flying around in space around the nucleus of the atom. And when they get pulled out of orbit and into the nucleus, it's called electron capture. We're going to use that beta symbol again. It is an electron now. We are working with an electron. So there's that E with a -1 charge or a beta with a -1. Either one is perfectly all right. Once it gets into the nucleus, that electron is going to combine with a proton, and it's going to form a neutron. So it's like the positive and negative charges cancel out. It's the opposite of a beta emission. So before a beta emission, we had a neutron breaking or splitting into a proton and electron. Now, we have a proton and electron combining to form a neutron. Those two negative charges wipe out, and the mass of the proton stays, and you have a neutrally charged neutron. Take a look at a couple of examples here. Thallium-232 decays through beta emission. So here's our thallium. Again, I use my periodic table, TH, the 232 right here. That's my mass number. It goes up here. I find thallium on the periodic table to find the 90. That's its atomic number. So it goes through beta emission. Here's my beta particle. I can use my little e, or I could use my Greek symbol beta. Either one's correct. But make sure we have a positive charge down here this time. Again, the rules are still the same. My numbers on top have to add up. So 232 plus 0 is 232. And then in order to get to 90, if I have a positive 1, I must also need 89. So I use my periodic table. I find number 89, actinium. There's my symbol, AC. Actinium-232. Another example, nickel-59 decays through electron capture. Okay, watch out for this one. Here's my nickel-59. Again, I found the 28 on the periodic table. Plus, this time, my beta particle, my electron, is on the reactant side. So that's kind of the difference here with electron capture. The beta particle is a reactant. So this time I don't have my starting element arrow. This time I have the starting element plus the beta particle. Now we'll have the arrow. Otherwise, all the rules are still the same. My numbers on top need to add up. So 59 plus 0 is 0. 59 plus 0 is 59. And 28 plus -1 is 27. It's more like a 28 minus 1 because it's a negative. So again, I use my periodic table. I find number 27. That's cobalt, CO. And there's my electron capture example. All right, changing gears a little bit, fission and fusion. You've probably heard these terms before. If not, not a big deal. Fission is the splitting of a large nucleus into two smaller nuclei. So there's that picture. I always look at the eye, I look at the dot above the eye, and I think of that dot splitting into two. One dot splitting into two. So fission is what we currently use in our nuclear power plants. and it was the technology we used during World War II and our atomic bombs then. Fusion is a little bit different. Fusion is the combining of generally two smaller nuclei to form a larger nucleus, one larger nucleus. And I always think of the O here. I think of that German symbol that has two dots above the U. And I think of those two dots colliding in fusion to make the smaller nuclei. So one dot for fission, one dot explodes into two dots, fusion, come together. The U, they come together, the I, they split apart. Fusion is what's occurring inside of our modern nuclear weapons, as well as in the sun. Currently, we cannot contain the energy. It's just too much. We can't harness it, so we can't use it in a nuclear reactor. So there's your lesson today. We learned electron capture, we learned positrons, and then we finished it up with fission versus fusion.